So this will be the last video on chapter 5 where we will explore the normal forces on tilted surfaces. As of now, we have considered the surface to be horizontal, but now the surface is inclined. Even though the surface is inclined, the normal force is still at right angle. And for the time being, we are not considering friction. Okay, other than the normal force, the only force acting on the person is the gravity force in the vertically downward direction. And in these kind of situations, we generally choose coordinate system like this, where one axis is parallel to surface and the other axis is perpendicular to the surface. Now let's take an example to understand it better. So in this example, we have a child of mass m. He rides on a toboggan down a slick, and this angle of inclination is theta with respect to horizontal. Now we need to find the acceleration of the child, and in the B part we need to find the normal force exerted on the child by the toboggan. So let us first make the free body diagram for this child. Now his weight force will be acting in the vertically downward direction W, right? And the normal force is still perpendicular to the surface, so this will be the direction for the normal force N, and this is perpendicular to the surface. This angle is 90 degrees. Next, I'm taking coordinate system like this. This is our positive x-axis and this is the positive y-axis. Now it's very important to look here. If this angle is theta, this angle will also be theta. Let's understand this concept by using this triangle. Okay, so here we see that this is a right angle triangle and this angle is theta, right? And W is vertically downwards, N is perpendicular to the surface. Now if this angle is theta, so this angle will be 90 minus theta, right? And this total angle is 90 degree, so this angle will be theta itself, right? Now we can get back to the free body diagram. So what we can do is we can make components of the weight force in the x and the y direction. So in the x direction, the component will be W sine theta, and in the y direction the component will be W cosine theta. Now in the A part, we need to find the acceleration of the child. Now to find the acceleration, we have to consider the motion in the x direction. In the y direction there is no motion, the net forces we have 0. So since the child is moving along the x-axis, so motion is in the x-axis. Okay, so for that we can use the Newton's second law of motion. So sigma fx, this would be equals to mass times ax, right? Now in the x direction we have only one force, that is W sine theta along the positive x. So we can write that fx, we have only one force, W sine theta, and W we have mg, weight is always equals to mg, so mg sine theta. Now we can put here, so mg sine theta, this is equals to m times ax. Now from here we can see that this m and m will cancel and we'll get the expression for ax to be equals to g sine theta. And in the y direction, ay is 0 because there is no motion along the y-axis, so ay is 0. Therefore the total acceleration, or A, will be equals to g sine theta, and this will be the answer for the A part. Now in the B part we need to find the normal force exerted on the child. Okay, so for that we can consider the y-axis, and along the y-axis the acceleration is 0, so we can write that sigma fy is equals to m times ay by using Newton's second law. Ay is 0, so this whole term is 0, or we can write that sigma fy is equals to 0. Now we have taken this direction to be positive, and so this will be negative. So sigma fy, this will be equals to n minus W cosine theta, right? So we can put here, this is n minus W cosine theta is equals to 0. Now W is mg, so n minus mg sine theta is equals to 0, or we can write that the expression for n will be mg sine theta, and in vector form since it is along the y direction, so multiplied with the unit vector y cap. Now I'll be giving one practice question to you. So in this practice problem, you can see 4 identical bricks that rest on a tilted surface. Now you have to rank the bricks in the order of increasing normal force exerted on them by the surface, and you have to indicate where ties occurs. So this is a practice problem you have to attempt in the comment box below. And with this, the chapter 5 is completed. Now we'll see the chapter summary. Okay, so the first thing that we discussed in chapter 5 was force. Now force is a pull or a push, and force is a vector quantity. Then we discussed mass. Mass is the quantity of matter contained in an object, and it determines how difficult it is to move an object if it is at rest, or to bring the object to rest if it is in motion. Okay, now next we discuss the Newton's first law of motion, and it says that if the net forces on an object is zero, its velocity is constant. This law is also known as the law of inertia. Then we discuss inertial frame of reference. So inertial frame of reference is the frame of reference in which law of inertia is valid. Now next we discussed the Newton's second law of motion, and according to this law, if an object of mass m is acted on by a net force F net, it will experience an acceleration a that is equals to the net force divided by the mass of an object. And in component form we write that sigma fx is equals to m times ax, sigma fy is m ay, similarly sigma fz is m az. Then we discuss the free body diagram. The free body diagram shows all the external force acting on an object. And then the Newton's third law of motion, and it says that for every force that acts on an object, there is a reaction force acting on a different object that is equal in magnitude and opposite in direction. Then we explored the contact forces. Now contact forces are the action-reaction pairs of forces produced by a physical contact of two objects. Then we saw the forces in 2 dimensions, where we discussed that Newton's second law can be applied to each component of a force separately and independently. Then we discussed weight. So weight is the gravitational force exerted by the earth on an object, and on the surface of earth the weight of an object of mass m has a magnitude W equals to mg. Then we saw the apparent weight. The sensation of feeling heavier or lighter in an accelerating elevator gives rise to the concept called apparent weight, and it is the force felt from the contact with the floor in an accelerating system. And finally we discussed the normal forces, a force exerted by a surface on an object which is always perpendicular to the surface. So with this we have completed chapter 5. Now we'll start discussing the questions given in the book James S. Walker.